Are there any questions so far? Yes.
So when you write the gyro resonance condition, what is the physical significance like?
It is in the co-moving plasma. If you take the Doppler shifted frequency of the radiation, it should match the local cyclotron frequency.
Okay, so omega is defined in the
lab frame. Everything is defined in the lab frame.
Okay. So in the Doppler shifted thing, I can understand that omega minus k parallel v parallel.
Yes.
But that omega c by gamma, how does that come?
Omega c by gamma. This is the gamma is in the rest frame of the fluid. Gamma is the random motion. So you go to the rest frame of the fluid, but the particles are not at rest. Particles still have motion of gamma in that frame. So you go to bulk rest frame of the fluid, but particles have random motion of gamma.
So that's an average gamma.
Yeah. No, yes, you can call it average gamma. Yes, you're right. In average, in the sense, it is random, so it is not average velocity, but it's average velocity.
So, and another question is, what is the physical significance of is S plus minus 1? Like, what does it signify?
Electron and positron.
Okay.
Charge.
So S contains the information about charge.
Yes. In case of electron, you will have one sign. In case of positron, you will have the other sign.
So in general, in a electron-positron plasma.
Yes.
So which has this negative sign, electron or positron?
I think if you put negative sign here, it goes to the other side. It is omega c. So I think electron will have negative sign.
Okay.
You have to check that, but I think that is correct. Okay. Any other questions? All right. So I will then leave this now. This was a compendium of various physical processes as well as plasma conditions that we described. Now, as far as model of radiation in pulsar magnetospace is concerned, I will start with high energy radiation. Now, radio emission, as I mentioned, is far more difficult to model from first principles because of coherence conditions. High energy emission is somewhat easier, but even then, it has taken a long time for the subject to even make a little bit of progress towards understanding. So today what I will do is I will discuss one landmark paper, or a couple of landmark papers in the context of high energy emission from pulsars. It's not because that what the paper says is absolutely gospel or right, but it identifies the whole slew of physical processes and how they may interact to generate high energy radiation. I have shown you magnetospheric simulations from force-free magnetosphere condition, which have progressed nicely, and it tells you regions where you can get acceleration zones and so on. But in these papers, you will also find some crude estimate of where the radiation is coming from, what the photon density is, and so on. Those you have to take only as indicative. They are not detailed ones. What they do is they just identify the regions where there is uncompensated electric field, and you just arbitrarily assume a pair multiplicity, and from that pair multiplicity you then get a average value of Lorentz factor, and from that Lorentz factor you create curvature radiation. That is all that is done. But in reality, process may be far more complex, and even pair multiplicity need not be the ones assumed in these papers. So when you see these diagrams of radiation density in these papers, you have to take it as basically markers of zones where this radiation is created. Not in detail about what the particle energy spectrum is, what the physical processes are, and what is the output radiation spectrum that you will get from this. Okay, so just keep that in mind. So that step is yet to be taken from the magnetospheric models to real radiation models, even for high energy radiation. But what it does allow you to do is to get the geometry of the region and therefore get the beaming pattern. So beaming pattern is not so critically dependent on the actual physical processes that go on, but mainly on the geometry of the emission region. So therefore, that you can still reasonably well get from this magnetospheric. Okay. So what I'm going to discuss today is what's called the outer gap model. This was proposed by Cheng Ho and Luderman in 2 back-to-back papers in 1986. In the first paper, it discusses mostly the magnetospheric geometry, and in the second paper, it discusses more about actual emission mechanism in the context of Crab and Vela pulsars, and it also argues how the radiation mechanism would differ between pulsars of different periods and magnetic fields, such as in Crab and Vela. So that's the context of these 2 papers. So let's try to go through a little bit of what these papers actually set out to explain. Okay. Now this is a picture which you will be familiar with by now. You have an oblique rotator, and in the oblique rotator you have omega here, magnetic axis over there, and you have these lines of charge neutrality. So you have one sign of charge on one side of it, the other sign of charge on the other side, as far as Goldreich-Julian charge density is concerned. And in this hatched region, you have the closed magnetosphere, the field lines which close within the light cylinder. Now let's take one of these null surfaces. These null surfaces are such that, suppose you have a pair, and let's say we release that pair on the null surface, then immediately the 2 members of the pair will go in 2 opposite directions and will separate. So it is therefore easier to create charge depleted zones around the null surfaces. So null surfaces can be used as an indicator of the point where a gap begins to form. So you can start a gap here, and depending on what is happening downstream, the gap can then extend. Whether you are able to keep the magnetosphere filled with plasma or not, that will decide whether the gap exists or doesn't. Now, the assumption in this, or the argument in this outer gap model paper is that, let's take some hypothetical regions where I assume for a moment that there is uncompensated electric field. Now, to fill these regions with charges, you must have pair creation in situ in those regions. Why? Because except for field lines passing through these regions, you cannot have charged particles created in one region move to another region across the magnetic field. Charged particles can only move along the magnetic field. Okay? So primarily the volumetric distribution of charges will be created by radiation that comes from somewhere else, creates pair in that region, and then the pairs are localized over there. Now, in this diagram, 3 different regions are indicated, hypothetical regions, A, B, and C. Now, what you can see is that, let's say we produce radiation from any of these regions where charged particles exist. If the charged particle doesn't exist, there will be no radiation produced. So let's take radiation produced from the boundary of this region. Now, particles, as I said, are moving with large Lorentz factor along the magnetic fields. In the rest frame of this particle, even if you take isotropic distribution of radiation that is produced, in this frame, that radiation is strongly beamed in the direction of motion of the particle. Now, given a certain electric field, you will have acceleration of electrons and positrons in 2 different directions. So basically, you can have radiation which is produced either outgoing along the magnetic field or incoming along the magnetic field. So you take a tangent to the magnetic field and radiation is produced along that, and it will be either outgoing or incoming. Now, as you can see from this diagram, that there will be various field lines from which you can produce electron-positron pairs, which will eventually end up in these regions. And once they, produce photons, which will eventually end up in these regions. And once they end up in these regions, you can produce electron-positron pairs there, and you can then quench the electric field which is present. However, if you have a region which is just hugging the last closed field line, and you have a uncompensated electric field over there, then it is very difficult for this forward going or backward going photons created anywhere in the magnetosphere above it to penetrate this region. Just try taking tangents to this and then see where they end up. So just around the last closed field line, you can have a region which is not easily filled with electron-positron plasma. So therefore, an uncompensated electric field, which we call a gap, can exist all the way around the last closed field line, going down all the way to the light cylinder. The inner boundary of this will be the null surface, because inside of that you still have particles which you can which can fill this region. So from null surface till the light cylinder, you can sustain a gap. So that is the argument in this paper. Now, why this is still relevant in the context of global magnetospheric solutions that we are seeing today is that this region is also coincident with what we have called the separatrix, the current sheet.
Right.
And that is where, even in the present day force-free numerical magnetospheric solutions, is where the acceleration zones lie. Okay? So therefore, whether or not you believe this kind of local argument for electric field and pair production, even from global solution of the magnetic field, you do have a region which just hugs the last closed field line, and you have an acceleration zone there.
I have.
Yeah.
So, so when we were looking at this global magnetospheric solution, so we have seen that though it's force-free, but E dot B is, it is taken that it's approximately zero. It's not completely zero in this open field line region also, right? So, can that small finite amount of existing electric field in that region could also means possible to give this kind of gap which is created above the closed magnetic field lines?
No, where? Here or all over the magnetic
No.
field?
Just over just this between this white region, the region A.
Yes, region A is the separatrix where E dot B is definitely not equal to zero.
Yeah, it's not definitely equal to zero, and that
It
is
is not even approximately equal to zero.
no. When we are solving this, when we are solving for this, okay. So when we are solving this,
See, when you are solving for the magnetospheric solution, you end up with a singular region
right?
where E dot B is definitely not equal to zero. Okay, so that singular region in the ideal form of the solution has zero width,
Yes.
right?
Yes.
So that is how you can
It's basically
remove it out as a singularity. But of course, in reality, it will not have a zero width. You need this region for the return current to be present, right? So this current sheet will have to exist so that the boundary condition across this is satisfied, right? And as soon as they have a finite width, it will resemble something like this. And E dot B is not even close to zero over there. It could be very large, right?
no, but globally when we give, we apply these conditions, right?
That is outside this region. So
Above.
this, yeah, above and below.
Yeah, so it's only this line where there is a flip of.
Yes, so this is a similar line, right? So that similar line, you attribute a small width to it, it will look exactly like this, right?
So has any kind of means when people do this global numerical simulation, they also get the information about this the trajectories, magnetic field lines. Right?
Yes.
So when have anybody done like this? Means when they take a photon and they move something special to the geometry that they can no way can quench this region.
In the global magnetospheric solution, you don't need to quench this region.
It automatically comes.
It has to be present, which is an unquenched region has to be present for the solution to exist. Right?
It's a automatic solution which comes out of it.
Yeah. Okay.
And the return current is, you said it's coincident with this region?
It's coincident with the.
Isn't that, aren't the charged particles in the return current affected by the high electric field there?
Yes, it will be not only affected, pair cascade will happen. You will have the entire energetic particle and energetic photons will be traced by this region. Actually, maybe if I go back, you will remember this picture. many slides ago, so maybe wrong. Okay. So let's take this. Okay. So this is basically that separatrix, which is now just now assumed a certain amount of width in the solution. And you have, if you do, if you expand this region, you have these regions where you have large charge density, because here GR is also included.
Right.
So that way even the polar cap is not fully compensated. So you have some from here, and this is the base of this last open field. And this then continues outside the magnetic field.
Okay. The charges in the return current are accelerated and they radiate.
Yeah. So then if you convert that to photon density, you have this and you have this separatrix which is showing up here, and it's not showing up in the projection too well, but these bright spots, they are part of this separatrix which comes all the way to the internal surface. So this photon density, as I said, is a sort of indicator only. This is not a detailed calculation of the radiation mechanism. It's just certain assumptions put in. So this region and the region that I'm talking about today is coincident.
How do B and C come up?
No, this is just a hypothetical exercise. Suppose I have a gap here, suppose I have a gap here, suppose I have a gap here. I can show that B and C cannot exist, but A will exist. Okay, so now that we have said that, okay, so there is an acceleration zone around the last open field line. What is the consequence of it? Now there is an acceleration zone, means that the number of particles, actual charged particles there, are relatively small compared to the Goldreich-Julian charge density. Or the net charge is smaller than the Goldreich-Julian charge density. So number density of particles is a bit small. At the boundary of that region is where the charged particle density is building up. That's where you have large number of charged particles. So the radiation will primarily occur in these regions where charged particles are present. And let us take the boundary of this gap region. So you will have photons which are emitted. 4 different points are taken here as example. Emission here, emission there, emission here, emission there. So photons will be emitted by the 2 species of charged particles. One going this way, one going that way. 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 As we will see later, radiation from these regions just outside the outer gap will be the primary carrier of high energy luminosity. So these are the photons which will escape. Not every photon. It will go through pair cascade, and then eventually the photons that will escape from this region will carry most of the high energy luminosity. So you get beams from different parts of this region directed in these different ways. So this will allow you then to build a model for a given inclination of the distribution of the radiation pattern in the sky. And then you take your line of sight, put your line of sight at any angle that you wish, intercept this radiation pattern, and that should give you the high energy pulse profile. Now this exercise of finding the high energy pulse profile therefore depended mainly on this geometry and not so much on the detailed emission mechanism. Because all we have used here are the fact that the particles that are generating this radiation are highly relativistic and they're moving along the magnetic field. So this attempt was already begun in this Cheng-Ho-Rudaman paper and has been elaborated further in later papers. So there are certain effects which one needs to keep in mind. One is that you have certain field line, but as you approach the light cylinder, now we are talking about emission along the gap which is going all the way up to the light cylinder. So as you approach the light cylinder, there is a sweep back of the field lines. So the field lines, if you look at it from above, let us say, if the field line would have been straight in a non-rotating object, near the light cylinder the field line will bend. So this effect will have to be used in modeling the phase of the emission that the observer will see. So this picture on the right shows you that the situation when this emission 1 is pointing towards the observer. You can see that this emission 3 also is pointing towards the observer. So you see this emission and this is at a different point of time. This is at one point of time when this is pointing towards the observer, and at a different point of time when this has rotated a little bit more, this is going to point towards the observer. So if I want to know how long it will take,
So this wiggle line separating these two is basically two different times.
they are two different times.
Otherwise, magnetic field can't.
Yes. So with respect to this, this is an earlier time by 510 phase, and this is a later time by 530 phase. Okay. So this is just to say that okay, I take this and I go to the rotation phase where this is pointing towards me, and I take this and go to the rotation phase where this is pointing towards me. So there is a difference in rotation phase between these two to be directed towards the observer.
Okay, so is it like this? See the emission line point 2 and point 4, they are coming at one particular period.
Period.
Yeah.
Period is the same.
No. No, it's in one. Suppose in rotation number 1.
Yeah.
Suppose in one rotation.
We will
These
see
three-
1 at certain time, 2 at another time, 3 at another time, 4 at
Four,
another time.
but in one. But 3 and 1 will be much less separated in time than 1 and 2.
No, that's because we have drawn it that way, right? So there are, yes, so you're right, in the sense that there is an emission by, so this is an emission by inward going particles.
Right.
This is an emission by outward going particles. So what this is telling you is that if this, let us say, was an absolutely straight field line, then in this picture the inward going particle and the outward going particle will, emission from both will point towards me at exactly the same time. If I take the diametrically opposite part of the field line, so inward going particle emission from region 3 and outward going emission from region 1
Will come at the same
will
time.
come at the same time. If there was no effect other than just unmodified
Magnetic field.
dipole magnetic field geometry, right? So there are other effects which will make this not point to me exactly at the same time, but at different phases. Okay. So one is this sweep back of the field line, the other is aberration. It will come
Yes.
later on. Now, how much time will elapse between 1 and 3 reaching the observer? Is 510 plus 530, or if you ascribe signs to them, then it is 510 minus 530, but my 530 is negative. Plus delta D divided by C.
Yes.
So that is going to be the time difference between okay, so 510 minus 530 times the period plus delta D by C is the time difference
that's the
between the
time.
two of them. Okay, so if you take the period in and write only the phase, then it becomes delta D by RLC. Okay. Right. So you can then go along field lines and then construct this arrival times and construct a pulse phase profile. So here is,
I have one doubt. So so it is at particular time slice at one time at one point of time in space. Now we are moving along the magnetic field line and we are getting delta phi for each of the points, right? And then what we do, we add up this phase, like
you don't add up the phase, you just put them as a function of phase when you are receiving what, and then you can bin it in phase and then add whatever you are getting in each phase bin. That will give you the profile. You have 0 to 2 pi phase,
right.
and for each of these you know what phase it is coming. So you take
Okay.
the distribution of these in phase, and
So
that's what
basically,
gives you
along the
profile.
magnetic field line, we get all the value of phase and then bin it in how many ways, then make the histogram of that phase.
That is right.
Then we get the normal pulse profile what we observe
Yes.
matched with that.
Yes.
Okay.
So this illustrates the effect of aberration. There is aberration because there is a speed of the emitting region across your line of sight. And that speed actually depends on how close the emission region is to the pulsar itself. The closer it is, the smaller is the speed. The further it is, the larger is the speed. And here you have omega in this direction, so this whole thing is rotating like this. So the closer you come to the light cylinder, the larger will be the aberration. So if you take this field line, and let's say the emission is emitted along this field line, because of aberration, this will now appear to come in this direction. So the further away you come from the pulsar, the more will be this bending. Okay. So here they have shown few points, 1, 2, 3, 4, 5, 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. And then look at the arrival time of these in phase. And you can see that the arrival time will be 5, 4, 1, 3, 2. Then a gap, followed by 2 prime, 3 prime, 1 prime, 4 prime, 5 prime. And now you can try to do phase billing. As you can see that as you go this way, the distribution is widening out. As you come to this edge, the distribution is closed in. So you'll get an emission profile which will look like this. And similarly on the other side it will look like that. So this is what Cheng-Ho Ruderman did in this paper to show that you will always get a double profile, and it will have a build up and then a drop and rise again and a drop. At this point they did not try to do a detailed match with the actual radiation profile that is seen, although they show that there are pulse profiles of Crab and Vela at high energies which have this type of characteristics, not exactly idealized distribution of this kind. But this has been done later with more detail of the accounting for different emission regions along the fields and along the outer gap. And this is a paper by Romani and Yadigaroglu starting with that, and then other people have done it later. So there you now take the outer gap retaining surfaces, in a 3D plot, it looks like this complicated surface, and then you look at the distribution of the emission in space. So this is 0 to 180 degree viewing angle, and this is pulse phase, and this is the distribution that they predict from the geometric modeling of the outer gap. So now you can take your line of sight and put it at whichever angle of your choice, and then cut it and then see what kind of emission profile you see, and you begin to predict emission profiles of this kind. Okay, and this can then be compared with.
So here they
Actual
took
profile.
all this magnetic field sweep back and everything.
Yes, yes. So
But
this is
if there
all
was
complete calculation.
if it was a purely dipolar, then the profile would have been completely symmetric.
Yeah. So you can see the sweep back, right?
How are they getting the hard X-ray and gamma rays separately? Are they just assuming different heights of emission?
This is assuming different zones of emission, which I will come to a little later. So this part is attributed to the polar cap.
Attributed to?
Polar cap. So you have soft X-ray emission, which is the heated emission from the polar cap, and the radio emission is attributed close to the stellar surface, so it is more or less aligned with the polar cap emission in soft X-rays. And this is the other pole. Now here you don't see this because this is a picture on this line of sight where it doesn't cut this. But at some other line of sight you might cut this. And then you see that emission, maybe not this emission, or in some specific line of sight you might see that. So one can play around with this, with the geometry and then all this different emission fields.
What kind of field geometry did they take from the simulations?
No. This is long before this, 1992.
Right. So
This is dipole. This is what is shown here. The field geometry, pure dipole, and then sweep back electrode.
okay, how do they calculate the sweep back?
The beat.
Yeah. So basically, you will have to take the amount of toroidal field that you are generating, which I discussed in Goldreich-Julian itself. So you add the toroidal field to the poloidal field, and then you will get the local direction of the magnetic field.
They used the toroidal fields that were just like in the Goldreich-Julian.
That is correct. So basically, you get in toroidal field. I think the assumption we here the toroidal field is equal to the poloidal field at the light cylinder, and then the toroidal field drops as you go closer to the surface in the same manner as in Goldreich-Julian solution. So at the light cylinder you have
Does this match with the simulations?
no simulations will have somewhat different geometry.
Okay.
No, because again this is not a global solution, right? This is a local solution, and basically stacked up local solution over the entire magnetosphere. So therefore,
it may not be the accurate picture.
yeah. So there is no force free condition applied here or anything like that, right? So you're just trying to do a small local job and try to anticipate the local condition, and then do that all over the magnetosphere.
So the present day, the technique is still valid for the magnetosphere solution that they use.
Yeah, so in the magnetosphere solution, now you have a model of what the emission region is. You can redo the same thing, now with the separate tracks, now with whatever emission region you produce. And then you can then predict what beam pattern you will see from those, right? So the first attempt to that, in doing that was from the force-free magnetosphere solution, which Spitkovsky did some years ago. Bai and Spitkovsky then calculated from that magnetosphere solution what kind of sky distribution of emission that you would see. They called it the annular gap. And so annular gap, given a slightly different combination of angles, will produce very similar pulse profiles as outer gap does. So as far as the observed geometry of pulse profile is concerned, I think outer gap can model Crab, Vela, and other small number of pulsars for which this has been tried. So there is no difficulty with this. You will come up with a certain solution of a combination of angles, all these geometries, right? But if you go to a different magnetospheric solution, you will still be able to explain it, like in the force-free solution. The angles will be slightly different, but you'll still be able to match the observed solution. Discriminator will lie in other detailed quantities like spectrum, polarization, and so on, which could be very different in these different predictions. And in the magnetospheric, the global magnetospheric solution predictions, at the moment you do not have a reliable prediction for spectrum, because detailed emission processes are not all accounted for. Here, one of the main effort in Cheng Ho Ruderman paper is to actually produce the spectrum. So they have gone through this full calculation of emission, the different emission mechanisms that we put in and so on. And then look at the escaping radiation and try to get a spectrum and try to match it to those emissions. But in the global magnetospheric solution, this will still be a bit of an ad hoc match. But these are things which need to be done. Right? So if you have a global magnetospheric solution, now you can start from there and do the detailed stuff that has been done for outer gap model or any other model. Right? So that is a step that is not yet there, but I guess it is not far away that such solutions will now begin to emerge. And secondly is polarization. Polarization expectation may also be different. In case of the global magnetospheric solutions, for the radiation that comes out from outside the magnetosphere, outside the light cylinder, polarization predictions are quite robust. Now, if the radiation is dominated by what comes from outside the light cylinder, then you have a pretty good prediction of polarization coming from the global magnetospheric solutions. This, of course, has no component from outside the light cylinder. Yeah, so all this emission is within the light cylinder. So therefore, the polarization prediction of this will absolutely not match with that of the global magnetospheric solution from outside the magnetosphere. Now, I have mentioned this when I was talking about the global magnetospheric solutions, that in the current models, the magnetosphere is what is called a FIDO. Force-free inside, dissipative outside light cylinder. So most of the dissipation currently is attributed to outside the light cylinder. These separatrix regions and so on, although they are populated by high energy particles and although they produce radiation, in the total radiation budget, that contribution is a small fraction. So therefore, there is a distinct difference in the prediction of this outer gap model and the global magnetosphere solution models, because the radiation zone in the global magnetospheric solution models have been moved out of the light cylinder, primary radiation zone.
So what are this? I mean, so when you say that they have this pretty robust prediction of polarization if it's coming from outside, but oh well, though nobody has done it for if it is coming from inside, right? So then there is no way, no such distinctive difference right now one can say about that. What
no, but at least qualitatively you can say, because
so what kind
inside what is happening is that you have emission coming from a whole range of magnetic fields which change in direction.
Right.
So there is almost no way you can expect practically the same angle of polarization over the entire pulse period.
But outside that is the case.
Outside that is the case because the
just
polarization angle is just defined by the spin axis of the pulsar.
Yeah.
Right? So no matter what phase you are, the polarization is always aligned to the spin axis. So therefore, and since that is a fixed quantity, you will get a polarization which is more or less constant across the pulse phase.
This polarization in which band?
Gamma rays or high energy X-rays.
They have for sufficient number of pulsars?
One pulsar.
This one. Okay, only for crab.
Yes. But the prediction can exist for all. Measurement is so for only one. Right?
So now once if anybody see this now swing, that's what has been shown. What could be, because if it is going far, suppose if it's coming far away from the outside, far away from the light cylinder, it should be absolutely constant. It should not change at all. Now if it gets inside, then coming much in from...
No, this is a qualitative statement.
No, it's qualitative, but...
because you have to also take into account how the radiation is being generated. If the radiation is being generated through reconnection, for example, then the magnetic field may undergo a very quick
no, a helix.
very quick change of direction. And in that case, you will see that imprinted on the polarization as well.
No, see, if we go outside the light cylinder, so we have only the sweepback phi field, which is just wrapping around, right? And the charged particles are streaming out along that the one which are in the open magnetic field coming out and they're streaming out, right? Along the magnetic field lines.
Yes.
So,
So what
I
does that
cannot-
produce?
Huh?
What does that produce? It produces a current.
Right.
What kind of current?
It will be in a phi direction only.
Due to that current, what kind of field will be produced?
Poloidal.
So,
Oh, so now this poloidal and this toroidal means existing toroidal and the poloidal, they can again reconnect. And then at those reconnection point, you're saying that the new quick change in
yes.
the.
So the main field is actually toroidal.
Right.
Okay. So that is the main base field on which the radiation occurs. And it's toroidal in a plane which is perpendicular to the spin axis. So therefore, synchrotron radiation will always produce something which is parallel to the spin
Parallel to
axis.
spin, right.
But that is not the only component of the field. There is a component of the field which may be smaller in magnitude, but which is still poloidal. And that poloidal field can reverse direction and undergo reconnection. And you may see imprint of that in the form of variation of polarization around this field.
But there is one thing, see, these reconnection, right, they are very stochastic, right? Means suddenly they will happen, they might stop, again they will happen. Very quickly it will happen, right?
No, it might, there may be zones where it is continuously happening. And that zone will go in and out of your field of view.
So there has to be a very specialized kind of thing happening over there. Well, something very specific. Otherwise, how can a region which is happening means continuous reconnection happening only at the particular phase of the rotation, right?
Yes, so that will have to do with because it's a geometry which is not fully axisymmetric, right? Because there is a
Yes. Right.
So because of a large angle between the magnetic field and the spin axis, there are certain zones which are preferentially prone to reconnection than others. So it will follow the rotation of the star.
Is there any kind of work has been done in this?
Yeah, this is what people are doing.
It's reconnection and.
Yes, reconnection is one of the things people are doing. So in the strike-to-in model, these are the inputs which are being used. Anyway, so I am not discussing that today. I will come to that maybe much later. Okay, so coming back here, then let me try to finish up now. So now let us say that this gap exists, and assuming that this gap exists, we might be able to generate reasonable pulse profiles for high energy radiation. Now the question is, how is the high energy radiation getting generated? How are the pairs getting generated? How are they getting accelerated? Where are they radiating? In what is the mechanism of radiation? And so on and so on. So these are the questions one has to ask, and that's what this AutoCAD model paper does. So now let's take a look at the gap. So this whole picture is now separated into three zones. One is the primary zone where there is uncompensated electric field, and you have this is the estimated value of the electric field, and the potential drop from the inner edge of the gap up to the light cylinder is something like this, 2 times 10 to the power 15 volts for typical parameters. So if you leave a particle over there, then this electric field is going to accelerate it to 10 to the power 15 electron volts. But that is not possible. No particle can get accelerated to 10 to the power 15 electron volts as they move along the magnetic field line. Because as they move along the magnetic field line, they will do curvature radiation. So as you keep increasing its energy, the curvature radiation loss will increase. At some point, the rate of increase of energy due to acceleration and the curvature energy loss will become the same. So that will limit the maximum Lorentz factor that the particle can be can get. So there is a radiation reaction limited Lorentz factor that the charged particle will be able to attain. So now this charged particle, which has a high Lorentz factor, although it is radiation reaction limited, will produce high energy radiation. So this radiation can be produced in several ways. Curvature radiation, of course. Then if there is a radiation field present in this region, then it can also do inverse Compton. So these radiation mechanisms then produce very high energy gamma rays. These high energy gamma rays will travel in the magnetic field and then start producing a pair cascade. The region where the pair cascade avalanche picks up will be the zone where you will now have large number of charged particles produced and E dot B will drop. That signifies the edge of this gap. And it is at edge of the gap, the transition zone between high E dot B to 0 E dot B is called region 2 or secondary, where E dot B is present, but is much less than the E dot B over here, but it is not yet 0. And then further from that, you have zones which you would call tertiary. So what happens in these regions? So primary region, you what you have is an unquenched gap. You have extreme acceleration and you produce super energetic photons. These super energetic photons then travel. In the secondary region is where they are doing the major part of pair production. So this is a gap boundary layer. Major pair cascade is happening over there. Energetic gamma rays are produced. So you produce first generation gamma rays which are very high energy. They will immediately pair cascade. They can't leave that region. The pair optical depth is very high.
In primary.
In secondary region as well.
Yeah, in any way, those are extremely energetic, which are getting produced in primary. They are getting broken up there only, right?
If it gets broken up and produce a large number of pair cascade, then that is what the secondary region is. Because that will then limit the gap.
The classification actually.
Yeah.
When it goes up very high, it breaks. It's a secondary.
It's a secondary. Because you have now populated that region with particles. So, but as the pair cascade goes on, the photon energy will come down. But you'll still have energetic photons. At some point, for those energetic photons, this will become optically thin to pair production. And those energetic photons will leave this region. They are still energetic enough to produce pairs. But there is not enough space now for it to convert itself to pairs. So this radiation will escape, and this is the main source of luminosity of the outer gap.
I have one question. So when people look at this very high energy emission from crab, right? They have very high energy it comes, right?
Yeah.
In magic and others. So if anybody wants to attribute these are the photons coming from only this region, one can say. If this is
No, so there is a very small probability of very high energy photons
yes,
leaving this region.
Yeah.
But there are other ways you can produce very high energy photons. Okay. So we'll come to that by and by. some of these secondary photons will end up in other parts of the magnetosphere, which you call tertiary region. Now remember, you have beams which are produced by ingoing particles and beams which are produced by outgoing particles. Particles are still very relativistic here, and these beams are emitted along the tangents of wherever they are present. So, but now beams produced in one part of the magnetosphere by ingoing particles and beams produced in another part by outgoing particles, they will produce beams of high energy radiation which will end up as crossed beams and intersect in tertiary region. So in the tertiary region, you will have gamma-gamma collision and produce low energy pairs. And these low energy pairs, tertiary region has no acceleration because there is no E dot B. But these low energy pairs will be produced. Magnetic field is there. So in that magnetic field, these low energy pairs will do synchrotron radiation. Remember now, the pairs that are getting created now are not moving at high speed along the magnetic field. The pair creation has happened by gamma-gamma collision, so it is their direction of motion is controlled by the direction of the beams.
So actually,
Radiation.
so the new particle momentum, what direction it comes from the momentum of the photons,
Yeah.
right? And they have no other thing to redirect in other direction.
That is right. So therefore, you will get synchrotron radiation.
Right.
There will be a large magnetic field, and this synchrotron radiation will be more or less isotropic. However, the radiation frequency will be smaller. So it will be optical, infrared, and so on, depending on the local conditions. Now that these are more or less isotropic, some of these photons can come and illuminate the primary region.
Yes.
In the primary region, now have energetic particles which will then inverse Compton scatter this low energy radiation.
Again.
And this inverse Compton scattered photons can interact with other photons of low energy in the low energy beam, do gamma gamma and produce pairs. So this is a self-sustaining closed cycle. Primary produces super high energy gamma rays, goes to secondary where pairs are produced and crossed extra beams are produced, which end up in tertiary region where low energy pairs are produced and low energy synchrotron emission is produced. The low energy synchrotron emission illuminates the primary gap and then provides fuel for pair production. Okay, so I'll stop here today.